Welcome, everyone. Okay, so today we're going to be doing the Bernstein-Vazirani algorithm. That is going to be using the same circuit as the Deutsch-Hosa algorithm, but we're going to be solving a different problem. The problem we're met with here is we're essentially given a function f of x, and we want to determine the a in the f of x. So f of x is going to be a function of a, and it's going to be a function of x. And essentially, A is going to be an n-bit string. It's going to have n bits in it, n zeros and ones. And it's going to have this bitwise AND operation on the x here. And if you recall, the bitwise AND is an operation that does just defined this way. X1 and Y1, where this is the first bit in the series of bits. Again, X will, for example, be a series of bits, something like this, right? And this will be x1, this will be x2, this will be x3, right? So, and this is going to be the bitwise or addition modulo 2. Addition modulo 2. Addition modulo 2, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. That's all. Essentially, we're pretending there are only two numbers in existence, and when we overflow, we just flip back to 0. That's all we're doing. So this bitwise operation here, x2 plus y2, or not plus 2, and bitwise and, all the way up to the nth bit in the string. All right, that's all this means. So we have this this thing a, this n-bit string a, and we want to know what it is. And classically, we would need to make n queries where a is an n-bit string, where n is the size of the string. However, with quantum computing, we only need to make one query, and I'm going to show you the circuit to do that. You could probably remember it from last lecture, but just as a review and also as a refresher, we have just two Hadamard gates here to start off with, and then we have this special controlled functional circuit here, and then we have another Hadamard, and then finally we measure, and then we read the outcome here. And down here, we're just going to have a 1. But here, we're going to have 0 to the n. Now, this may look familiar from the Deutsch-Hosa algorithm, and that's because it's the same circuit, as I said. But right now, we're not going to be looking for whether it's a constant function or a balanced function. What we're going to be looking for instead is what this a is, this string of n bits. And recognize it could be n bits, and where n is any integer. So you would need to make n queries classically, whereas you only need to make one on a quantum computer. Now, I'm not sure how familiar we are all with complexity classes, but this is not a complexity class improvement by a quantum computer over a classical computer, simply because this, classically speaking, is not a hard problem. On a classical computer, this is not a hard problem. It can be done in polynomial time. So we're not seeing a complexity class improvement from a quantum computer, but recognize that we're going from n queries to one query. So that could be a very significant speed up still, even though it's not technically a complexity class speed up. Recognize complexity classes are a bit heuristic, so we're still saving a lot of time and memory here, even though it's not a complexity class speed up. So how do we actually execute this algorithm? Let's just take a look at how the thing goes. Um, yeah, so we put it through the first Hadamard gates. And psi1 is the state of the system after it goes through the first Hadamard gates. The bottom gate, when we take a 1 and put it through a Hadamard gate, it just kind of looks like this. The top is going to be a bit more complicated. We're putting a string of n zeros through a Hadamard gate, And what we're actually going to get out of it is something that looks like this. So on and so on. But we're actually going to represent it like this. Where x is going to go over 0 and 1. Double check my notes to make sure I'm not missing terms. No, all good. So that's what we're looking at after the first gate here, which is this. These first two Hadamard gates here. Next up, we have this. This is a controlled functional NOT gate. And after going through this state, psi 1, after going through, we're going to have psi 2. And psi 2 is going to be a little bit more interesting than this state here. Remember, these are the control bits up here, the top bits. And down here, what this gate does, this U of F, is if f of x is equal to 0, it does not flip the bit. If f of x is equal to 1, then it does flip the bit. That's how it works. It's sort of like in control NOT gate, where if it's a 0, then it does flip the bit and execute the NOT, where if it's a 0, it doesn't. If it's a 1, it does execute the flip and it flips the bit and does what a NOT gate would do, right? But instead of x, it's f of x now. So f of x is the control now. If f of x is 0, nothing happens. If f of x is 1, we execute the NOT gate and we flip the bit, right? So that's what we're dealing with here. And after this, remember, we've seen the Hadamard gate enough times that we can kind of abstract out now what's going to happen with it. In the last lecture, you saw this as f of x, but we can now make the replacement and say that it's going to be a of x, but it's actually the same as we saw in the last lecture. So I'm just going to write it out again. And this, again, this -1, a to the x here. If this exponent is a 0, then it's just a 1, and then it doesn't change the sign. If this is a 1, then it's a -1, and it does flip the sign. That's the function of this whole thing here. And that's going to be acting on x's. And remember, the x's can go over 0 and 1. The x is going to be a 0 or it's going to be a 1. It's just bits. Bits, specifically these kinds of bits, after they've gone through the Hadamard gate and been multiplied by each other and foiled out and things like that. This is the whole thing. And then we're just going to have the other bit. And of course, there's a summation here. And I'm omitting the normalization factors because we know what they are. It's just 1 over the negative, 1 over square root of 2. Okay, so at this stage, we, in the last lecture, saw f of x here. Now we're seeing a of x because we simply substituted f of x equals a of x for the function. Remember, last time f of x was the function we were trying to figure out whether it was constant or balanced. Now we're dealing with a of x in this little u of x controlled NOT gate functional thing here, right? So this gate right here is now operating with a of x rather than this f of x, which is kind of the mystery function that could be constant or balanced or not. Now it's operating with a of x. That's simply by design. That's the way we want the algorithm because that's what's going to tell us here. Okay. So now I'll redraw the last part of the circuit, but basically this is just going to go through another Hadamard gate, and then we're going to measure it. This top is going to go through another Hadamard gate, and then we're going to measure it. And finally, we will get this. Um, okay, I've written this out. A Hadamard gate acting on a general n-bit system here. This is just a relation that holds for generally a Hadamard gate acting on this x, which again, this x is going to be a string of zeros and ones. Any string of zeros and ones, just a general string of zeros and ones, and an n-dimensional Hadamard gate, meaning a Hadamard gate that is going to act on each one of these individually. So you can see this is going to be a mess. We're going to have to foil a lot of terms together, but this is a general relationship that comes out the other side when we're done foiling. And we're going to have this sign flip operator, and we're going to have the ith bit times the yth bit times yi, where the xth bit is the original bit that we're operating on, and the yth bit is what is the bit that's going to be transformed into by the Hadamard gate. So this is a little bit abstract, but the xth bit is going to be this mess that goes in to the Hadamard gate. The input to the Hadamard gate is the x, right? And then the y is what comes out, what the Hadamard gate transforms each bit into. So what this relationship is essentially telling us is that y can range over 0 and 1, and you have essentially this relationship. The -1 can be one of these four possible things. It can be a 0, 1. It can be a 0, 0. In other words, it can be the Hadamard gate can be taking a 0 to a 0, in which case it's a 1 and it doesn't flip the sign. This is correct, right? Because a Hadamard gate takes a 0 to a 0 plus 1, and it takes 1 from a 0 minus 1. So either way, if it's taking a 0 to a 0, it doesn't flip the sign. That's all good. If it's taking a 0 to a 1, we see that, again, it doesn't flip the sign. If it's taking a 1 to a 0, again, it doesn't flip the sign. The only situation in which it does flip the sign is when it's taking a 1 to a 1. And again, this makes sense because when it's taking when it's taking a 1 to a 1, it's operating on a 1. And when a Hadamard gate operates on a 1, it's taking it to a 0 minus 1. So this makes sense. So it does actually flip the sign in this case. So we're just abstracting that relationship out and putting it here in kind of this kind of form. That's all this is. It looks fancy, but it's not. So that we can move to this step here. Because you can see this. Oh, by the way, if you're not familiar with this term here, like this pi term here, or I'm not sure which Greek letter that is. I think it's an uppercase pi. This is a multiplication. This means these terms are being multiplied over and over and over again over the i's. So this is a sum, this sigma, and these are being multiplied over and over. So we're basically summing this relationship that I just told you. So basically just getting like, zeros plus ones, and if it's taking a 1 to a 1, then we're getting a -1, and then we're multiplying all these kind of together, right, over the i's, over I to n. So that's what this is doing, and this whole mess is going to come out the other side. We're simply going to kind of group together all the terms that were multiplied out, and we just want a sum. We want a pure sum. So we're just going to say this. However it comes out foiled the other side, it's going to look this way. Where this is this bitwise thing I told you about before. We've already seen this. Times y, right? Okay. So that's in general what a Hadamard gate does. This is just we're just defining this way. This should be 3, right? So we're just defining these FOIL terms. Each one of these in the sum is going to look like 0, 0, 1, 1, 1, 0. It's just going to be this, right? It's just FOILed out. That's all. Okay, so back to our psi3 now. If you recall with the psi3, we're putting it through this Hadamard gate here now. So we're going to use this relationship that we just derived. And we did this in the last lecture already with f of x, but we're setting it equal to a bitwise and x by designing the algorithm, because we're trying to figure out what a is, remember, in this variation of the problem. And of course, we still have the other bit. And let me just scroll down a little bit here. Gives a little more room. Okay, and then what do we have here? Okay, so this a of x and this x of y here. They have to, this y, unless it's this, and by the way, each one of these is a string of n bits, right? So if this string of n bits, this y here, is not equal to a, the string of n bits, then this is just going to go out and zero out. Because we have, this goes to 2 to the n minus 1, which is even number of terms because it's zero indexed. It starts with 0 and goes to an odd number, so it's even indexed. And these signs are going to flip back and forth, and they're going to cancel each other out. So the only way we can avoid this is if we have a of x, because then if these are the same, then they're going to have the same parity. So if it's -1, this will also be -1, and it'll be +1. If this is +1, then this will also be +1, and it'll be +1, and they're not canceling each other out. So in that case, the only one that's going to survive is when y is ax. So the only one that's going to survive here is this state a, right? And from a, we can recover what the bit is. We can recover what this ny's bit a is, and that's the way the algorithm works, essentially. Again, it's a significant speed up, not a complexity class speed up. There's one more problem called Simon's problem and Simon's algorithm, which is actually going to be, a full complexity class speed up. It's going to take, it's because it's an exponential hard problem. But we still see a significant speed up and a significant improvement in this kind of problem. So, okay, I think this was pretty comprehensive and straightforward, but you guys should be the judge of that. If you have any kind of questions, just DM me or drop a comment underneath the video. Thanks for listening as always, guys. See you later.